We're moving into chapter 8, dealing with friction. We are going to skip screws. We'll skip, I didn't even put the titles of these other sections in there, but we will cover wedges and belts as application, as well as a lot of other simple problems in dry friction. So this is an introduction. So you start, you put on a surface a block. That's easiest. You just put a block of height A and the width B, and it's 2D. You can make it 3D. Everything is truly 3D, but we just, for introductory purposes, 2D. The block has a weight, W, and it's resting on this solid surface. You do a free body diagram. There is a normal reaction between the surface. What is A? Height of the block. What is B? The base of the block. Okay. Where is W located? In the middle, so B over 2 and B over 2 on both sides. What is W? The weight of the block. And what is N? That normal force between the block and the surface. Okay, so if you did the free body diagram and took away the surface, you would have N pushing up on the bottom of the block. And what is the relationship between W and N? They're the same. How did you do that? The magnitude is the same. How did you do that? Well, you did it equilibrium. Sum of the forces in the Y must equal to 0. Let's pull on the block. Let's put a force P. Let's call it P, probably for pulling. It'll be applied at a height H from the bottom of the block. What is A? The total height of the block, so H is between 0 and A. Okay, so that's a force pulling, as is shown here, to the right. Would there really be much difference if it was a pushing force? Put it on this side? No, not really. Okay. And then H is that height that's applied. And then what is F down here? Friction. Yeah, it's a frictional force. You will have the block doesn't automatically start sliding. There's a frictional force between the bottom of the block and that surface, and it will be in the opposite direction. Okay. It's tangent to the surface. The normal force is perpendicular to the surface. So N and F are at 90 degrees with respect to each other. And P and F are opposite, just like the weight and the normal force are opposite direction. Okay. So, given A and B, what were they again? The height and the width of the block, and the weight of the block, and the height that the load P is applied. Given all of these, can you find what N is? And then what is the next one? F. And where is O? What do you mean O? That's the point O of application of N. It's really what is X. What is X here is the distance between where it was directly underneath the weight to shifting over to the right, X. How about this? Can you give me equation for N, equation for F, and equation for X? I'm going to pause, walk around. All right, so let me pick it up here. What we do is we say the block is in equilibrium. And if we do our free body diagram, this is really the free body diagram of the block, where W is the weight, you have the normal reaction pushing up, the load P, and the reaction of the frictional force on the bottom of the block F. And the proportions are given. If you do the sum of the forces in the Y, you get a simple reaction that N is equal to the weight of the block. So if it's a 200-pound block, the normal force is 200 pounds. And then if you do the sum of the forces in the X, what do you find? That the frictional force has to compensate for the load. And then you do, hey, we did this 2 equilibrium equations. There's a third equilibrium equation in 2D. We'll do the sum of the moments around a particular point. It really doesn't matter what point. All points will work. But a lot of people will do point O, which is right here. That's where N is applied. If that's equal to 0, then we find that the weight comes down and makes it want to rotate. So W times X makes it want to rotate around point O in the counterclockwise. And then you have P at a height h, makes it want to rotate in the clockwise around 0.0. N and F both go through 0.0. Boy, my illustration's getting all messy, isn't it? And so this is our equation. And so x is equal to h times p divided by w. Right? Right. Okay. Simple questions. Can the load P be applied such that h is greater than a? Yes or no? No, that doesn't make any sense. It would be applied up here in the air. No, it has to be applied somewhere along the block. What could be the maximum value for h? A. Yeah, it's good. It could go from 0 to half all the way up. So that doesn't make any sense. How are h and x related? Hey, we just did that, didn't we? So which one is the correct answer? B. Yeah. And how did that come about? Equilibrium for the free body diagram of our block, where we're considering the sum of the moments about any point. Pick point O, and there you go. Okay, here's another question. If P is increased, how will N change? How will N change? Will it decrease? If P goes up, will N go down? Will it remain unchanged, or will it increase? Unchanged. Now at first you may think, hold it, if I'm going to pull on this block, isn't it going to make the block want to dig in, and won't N increase? But it won't. If you have a different angle on P, if you pull up, N goes down. If you pull down, N goes up. Exactly. Good observation. Thank you. But right there, it will not change. It'll be unchanged. If P is increased, how will F change? It will go up too, and it's a 1-for-1 as we've shown. If P is increased, how will X change? Now we're getting a little trickier. Won't it move over and over and over and over? And just like I had the question of, can P be applied greater than H greater than A? You said, no, that doesn't make sense. Well, guess what? What's the maximum value for X? The tipping point of this crate is when X is equal to, what is it, A, B, or C? B. And can X ever be greater than B over 2? No, it doesn't make any sense. It would have tipped. It would have tipped. Okay. Now let's talk about maximum frictional force. I like to put F static max, but that's not used in the book and probably not used in the majority of literature. But I like to emphasize that Fs is the maximum static frictional force. Well, how do you get that maximum? It's a very old equation. It's the mu sub S times N. And now you say to yourself, what exactly was N? Is N the weight? Not always, because as we just talked about, maybe that load P is lifting the block a little bit, and then that'll change N, won't it? But a lot of times, if P is purely horizontal, then N is simply the weight. Often it is, but don't put the weight of the block in, put N, the normal force at that surface. Okay, and then what is mu sub S? It's a coefficient of static friction. Why do they have mu? Well, okay, Greek letter, we need to go to the Greeks to get more letters. And then subscript S for static. Okay, so coefficient of static friction, and that's our normal force. Typical values, there's a table in the textbook. When you see a table in a textbook, spend a few minutes just looking at the values and asking yourself questions about the values. Well, here we have metal on ice, 0.03 to 0.05, wood on wood, 0.3 to 0.7. Copper on copper, 0.74 to 1.21. Okay, this is quite a range, isn't it? This would be like the minimum value and the maximum value in the table. And if you look at the variability between 0.03 and 0.05, it's not that much. You know, but if you look at the variability between 0.3 and 0.7, it's even more, isn't it? That's quite a bit of variability, meaning that different woods and different conditions of the surfaces of the wood lead to different μ's, a wide range. It's not like a very single number that can be reported to 3 and 4 significant digits. If you look at these, this is down to 3 digits, but that's excessive. Copper on copper, it's a particular type of metal on a metal. All right, the coefficient of static friction can be negative. True or false? False. Yeah, I mean, it doesn't make it. Think about that. You would pull this way, and the frictional force would help you? No, it's opposite. It's always opposite, so it cannot be negative. The coefficient of static friction can be greater than 100%. True or false? Let's express these as percents. 3% to 5%, 30% to 70%, 74% to 120%. I'm going to forget that extra digit out there. This is incredible. And a lot of people, that's probably one of the most missed questions. It's like, yeah, you can actually. It's rare. I didn't say it's common, but it's rare that you can have a coefficient of static friction greater than 1. Okay. And then the coefficient of static friction is empirical. Well, since I don't know the meaning of the word empirical, no, that's not how you answer questions like that. What does empirical mean? It's based on measurements. It's not a theoretical derived. It's like I have this coefficient, and then how do I go measure it in the lab or different places? And it's very empirical, so that's true. Okay. If the contact area increases, then the maximum static frictional force increases. You got more area? Well, then you must have a larger frictional force. But look at our equation. Our equation is Fs, that's the maximum static frictional force, is equal to mu sub s times n. Where is A in that equation? Somebody could say, well, it should be the normal force per unit area. That would be a pressure, right? Or a stress. But that's not the way the equation's written. Hence, there's no area in that equation. So if the contact area increases, then the maximum static frictional force increases. That's not true. It's not true. All right. And if the normal contact force increases, then the maximum static frictional force increases. That's true. See, it's proportional to n. All right. Let's go back to this problem. When P is less than the maximum Fs max, that's our maximum, our static, that's equal to mu sub s times n. Okay. When P is less than that Fs, the object will move in the same direction of F. The object will not move. The object will move in the opposite direction of P. B. Which one? B. B, yeah. The object will not move. See, this is our maximum, but our actual F can always be less than the maximum. When P is greater than Fs, let's say you find that the maximum frictional static friction force is 100-pound force, and yet to put on a 120-pound force, what's going to happen? The object will move in the same direction of P, object will not move, or the object will move in the opposite direction. A, yeah. So that's when you get slipping. We already talked about tipping. Tipping is when x gets greater than or equal to that b over 2. Okay? but you can also get slipping. These are states of impending motion. It's about ready to rotate, tip. It's about ready to slip, translate, and accelerate. Okay, that's when P is greater than the maximum frictional force. For this class, we're only going to think about, very briefly, slow slipping, no aerodynamic lubrication or anything like that, with fast slipping. And our simple equation looks like our equation for the static. So you have this frictional force when you're slipping is mu sub k times n. What's mu sub k? Well, it's not the coefficient of static friction, it's a coefficient of kinetic, like moving friction. And the book recommends or says it's about 75% of the static. So once you start slipping, it's actually easier to keep slipping. Okay? But because mu sub k is 75% of mu sub s. This is a rough number. Don't take it to the bank, so to speak. But if you need to do some simple calculations, there you go. So what we want to do, this is one of the most difficult plots I found in this textbook. We want to plot F versus the horizontal force P on our block. So we put on the y-axis F, and you can think about it in units of pound. Okay. And on the x-axis P, and you can think about units of pound. Again, here's our block. We're pulling with load P, and we get the weight of the block, we get the normal, we get this frictional force, the resist, the direction of impending slip. Okay, so if P is 0, that's the starting point, what's F? 0. But if you incrementally go up, 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 what happens is the frictional force goes up, 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 and this is a 1-to-1 relationship until you get up to something called Fs. I forgot. Fs, what's that subscript S indicate? Maximum static friction. What is our equation for that? Well, I'm going to write it backwards, but wasn't it mu sub s times the normal? Yeah. Now, once you get up to that point, you're at the point of slipping. You're at the slipping point. And let's say now the person continues to apply larger P. What's happening? You start slipping, and so it's going to fall down to Fk, which is mu sub k times n. And we said mu sub k is lower, 75% of mu sub s. And so it's going to do this. And now what's happening out here? Our P is getting larger and larger and larger and larger, but our frictional force remains constant at F of k. It's like our kinetic frictional force. And this is the split. Here is statics. Here is dynamics. This is this class. I can't spell nothing. CLASS. And then this is the next class. So we're up to the point of slipping. And then, hey, it slips. Great. But once it starts slipping, if P gets larger and larger and larger, what's getting larger? The acceleration gets larger and larger and larger. The rate at which the block accelerates to the right. Maybe that's why this plot is so simple for this class, and then we don't really want to worry about the next class yet. We'll worry about that. Drop off, or does it? Pretty sharp. Yeah, very sharp. And right in here, it would be a lot to study that. But what we have is a very simple model. It would actually be in this model, straight down and flat. Yeah. So with that, let's answer these questions, then we'll solve some problems. The blank static frictional force equals mu sub s times n. The actual, the maximum, the minimum, the tangent, or the perpendicular? What's the best? I think it's more of the actual versus the maximum versus the minimum. Okay, I'm going to throw those out. I just want A, B, or C. B, it's the maximum frictional force. Okay, the static friction force. When slipping is about to occur, the frictional force F equals F of S, meaning F equals mu sub S times N. Is that our equation for when it's about at that point of slipping? Yeah, that's true. So anything with P in there is garbage. And so we're down to A and D. And there it is. So sometimes it's like you get the equation F of S is equal to mu sub S N. That's true always. F is equal to mu sub S N. When? Only at the point of slipping, because F without a subscript is our true frictional force. Okay, the subscripts can be a little challenging. Let's solve some problems now.